Welcome to our first part of electrochemistry. So today we're going to learn what are the calculations involved in the electrochemistry so far. So when you come across this chapter in Malaysia, this is the second chapter of your second semester STPM chemistry. So when I teach students about electrochemistry, they often get confused because most of the things that involves in electrochemistry is entirely calculations. So wherever you go, you come across numbers, units, symbols, whatever, very large numbers and entirely calculations. But don't worry, I'm not here to panic here, but just to make sure you understand what is actually going on inside this calculation, other than just memorizing the formulas and all those different difficult concepts. No need. So you're going to see how easy this calculation is going to be, because we know that we've been exposed to such equations such as Q equals to IT, where your Q is the coulomb of charge and your I is your current and your T is your time taken, which is usually ended up in seconds. And we also exposed to another type of equation, which is Q equals to NF, where your Q is also the charge and your N is the number of moles of electron involved and F is your Faraday's. Okay, this is the very basics, and this will go into rotation. In every calculation you will always use this, especially in your electrochemistry. This is quite a famous formula that you must know. So let's get into this question, what we're talking about. In an anodization, they're talking about anodization. Anodization is a very famous one in your question papers, where they will keep asking you in a different manner, like how many coulomb of charge being used to do the anodization. Even some question even ask you to calculate the thickness of the oxide layer that is being added. This is kind of famous, right? So the anode is an aluminium object. If the aluminium object has a surface area, alright, good. The surface area is given, which is 5.0 times to 10 to the power of 2 cm square. How many coulombs of electricity? So this is the question. This is what you're going to calculate at the end. The Q. Okay, this is kind of easy when you look at the equations given that you memorized. It's kind of easy, right? Just by identifying some of these, you can get the Q. Okay, let's gonna see how easy it's gonna be. Are needed to increase the thickness of the oxide layer by 1.0. It's not as easy as we think, because the information here not very enough, that we don't have our current. Of course we don't have. They don't give you the time. No, they don't even give you the number of mole of electron. Okay, so without all these we're going to calculate the Q. Sounds impossible, but it's okay. We've also given some of the very tiny details down here. They give you extra information about the density. When it comes to density, there is a secret thing that is happening at the back. So you must know the very basic formula of the density. If you still remember, density is basically equals to volume. Not volume, mass or volume. Yeah, this is the very famous one. And we've given the molar mass of this aluminium and also the oxygen. Okay, and yeah, I know this one, guys, sometimes your question paper doesn't really provide you this at times, so you must keep that in mind, that 1F equals to how many coulomb of charge. All right, so this time they give you, they're pretty nice to you so you're safe. Okay, let's see how we're gonna calculate. So when it comes to this, you need to understand what is actually going on. So since I tell you anodization process, I need to explain to you how anodization happens and what is actually going on. So since this is your cell, alright, so this is your half cell and this is the entire another cell, alright, so over here is your aluminium. So of course when it tells you that your aluminium is your anode, so obviously when I say anode, the thing comes to your brain is oxidation. So anything sits in the anode place, even though different terminal, positive or negative terminal of anode, still the process that is happening there is oxidation. So if your aluminium being oxidized, you know what is happening, the Al3Al plus, and you have to donate the 3 electron. And since they mentioned in the beginning, they say it's an aqueous solution. Alright, so this one, imagining this solution over here, which is basically Al3O plus, which is aqueous, and the concentration is in a standardized 1 mole of DS meter cube and 25 degrees Celsius. So when it is aqueous, it also have a content of water. So water has the tendencies to either go to oxidation mode, or it has a tendency to go to reduction mode. So later I teach you how to actually identify when H2O actually undergoes this thing based on the SCP value, which is the standard electrode potential, and sometimes it's also based on your concentration. So that one is another video that I'm gonna cover. No worries, it's not that hard though. Alright, so over here the H2O have to undergo oxidation reaction. So how do we do that? So H2O have to remove the electron, so you're gonna form O2 gas plus H plus and electron. So you have to balance this out. So I put 2 here, I put 2 here, since there is a 4 hydrogen, so 4 and 4 electrons. Easy. Alright, so this is very easy. So we already know what is going on. And what about the formation of the oxide layer? The formation of oxide layer turns out to be that our aluminium ended up reacting with our O2, which turns out to give our Al2O3. So this is what exactly going on. So we can balance this out, and also this, and also this. Oh no, so it's not really balanced here yet, so it's a 4. So this is what exactly going on, and this is the formation of the oxide layer. Alright, so we already get this one done, so let's finish this off. Let's get into the question. So let's start calculating, which is the fun part. I really love this. So I'm going to use a blue pen, make you look it more easier. Pink is kind of hurt your eye. Okay, so since they give you the density, I always start off with the first things first. So density, we know that just now I said it's a mass over volume thingy, right? So but teacher, there is no such information given. If you want to put this inside the formula, you must either have a mass and you must either have a volume, but there is no volume. This is where the question play a tricky game. If you take a look at this one, 5.0 times to 10 to power of 2 cm square, isn't it? When you multiply this with the 1.0 times 10 to power of minus 3 cm, you see the thickness, you multiply with the surface area, you ended up getting the volume. Why I'm saying you ended up getting a volume? Because if you take a look at here, the cm square, you multiply with cm, you're gonna ended up getting a cm cube, which in turn tells you cm cube is more likely to be the volume. Easy, isn't it? Alright, so we're gonna look at the flow. We're gonna go step by step. So the first thing I'm gonna do here is calculating the volume of Al2O3 deposited. So you multiply 5.0 times 10 to power of 2 cm square. You multiply by 1.0 times 10 to power of minus 3 cm. So after you do some calculation, you're gonna ended up getting a number which is 0.5 centimeter cube. So here's the volume, and now you can insert this inside to get your your mass of Al2O3 being deposited. So density equal to mass over volume. For me, even though you are very get used to of these formulas, so in your exam you don't want to write down this formula, you want to straight go into the calculation, it's not wrong. But for me, I always encourage my students to write formulas first, because sometimes you can get confused. Alright, so over here I don't really write my unit because I already know what the unit is. So I'm just going to insert the numbers inside. So I would get my mass by 2 gram. So teacher, I finally got my gram. So when you get your mass, the thing comes to your brain immediately is the number of moles, because they already give you this molar mass. So the third thing that you need to calculate here is your number of mole of Al2O3 deposited. So still remember or not? Mass over molar mass, which is 2.0. So the molar mass Al is given as 27, Al2, right? plus with O3 16 times 3. So you're going to end up getting a 1 over 51 mole. So in a decimal form, you're going to get, I think over here, decimal no need. Just keep it as fraction, because you still have, if your significant figures is very less when you use decimals, when your significant figures is not enough, sometimes your answer could be wrong in terms of decimal places. So it's safe to keep it as fraction if the calculation still process in the process. Alright, so then after I obtain my mole, so later I have to insert this inside my, you know what I'm talking about, Q equals to NF, the fourth one. So I already get my mole right. But if you realize, I am so close to get my Q by inserting my number of mole. Very good. But for me to multiply this with the F, I need to count how many electron I'm using, right? Do not forget that, the formula. How many electron am I using? So back to the equation, guys. So going back to the equation, what is happening? So I'm writing back the equation right for you, where the equations are at anode 2H2O, the water is being oxidizing just now, O2 plus 4H plus and 4 electron, and your aluminium 4Al plus 3O2 2Al2O3. Sorry. So from this equation you can know that 1 mole of O2 requires 4F, which is 4 electrons. Alright, and then you have your 3 mole of O2 produce 2 mole of Al2O3, the oxide layer. So you need to identify how many mole we have to use to produce 1 mole of Al2O3. So 3 over 2 mole of O2 is required to produce 1 mole of Al2L3. And how do we do that, teacher? How did you get the 3 over 2? So based on the calculations I've made so far, so imagining you have this 1 and a 3 and a 4 and a 2, right? So same goes here. Imagining I have my 3 mole O2. This is how I usually do, producing 2 mole Al2O3, right? So I have my X mole of O2. Imagining now I'm calculating my number of moles of O2, and I want to know how much Al2O3 can be produced by how many oxygen. So I'm doing it this way, which you need to cross multiply until you got your X to be 3 over 2. So this is how I do. So if these things you think it's kind of complex and you have other steps, you may proceed as far as you get the correct answer. Alright, so then you already get your 3 over 2, and now you know that the last part, the last conclusion, you know that 1 mole of O2 requires 4F, which is 4 electron. So in this case you need 3 over 2 mole of O2, right, to produce your 1 mole of oxide. So you need to identify how many moles of electrons being used here. So I don't know, so I put that as a X, electron, or F. So use the same method. 1 over 3 over 2 equals to 4 over X, and your X is 6 electron. Okay, after so many observations and so many equations, finally I can make use of this formula of mine, which is the last step. Q equals to NF. Final step to calculate my Q by using the thickness. So my number of mole just now was 1050. Multiply with 6 times 96500. And the final answer of yours will you have 1.1 times the 10 power of 4 coulomb of charge. Finish. So this is too much of work here, so I hope you understand. You can even pause the video to understand what I'm talking about, and if you still don't understand, please click the link in the description box below that you will be taken straight to our Instant Dynamic Academy. For further details, it's our online tuition center, so you can join, and I have a trial class and free class, and see how you like the class or not. It depends on your convenience and your understanding, so we're not here to teach you whatever comes to our mind. No, it's all about your understanding. Your understanding is our priority. Alright, so I think that's all. So we see each other next week.